Now this next one has a little bit different of an approach and flavor to it. The statement is, suppose the electrically neutral YZ plane carries a time-dependent but uniform surface current KT in the z-hat direction. So, A, find the electric and magnetic fields at a height x above the plane if 1, a constant current is turned on at time t, or 2, a linearly increasing current is turned on at time t. Here are the two piecewise definitions for that. We have a constant current, K1, and K2 is linearly increasing, so alpha t. B, show that the retarded vector potential can be written in the form AX of t, AX and A of x and t is equal to mu c over 2 z hat, integral 0 to infinity, k as a function of the retarded time minus u du. Okay, and from this, determine E and B. C, show that the total power radiated per unit area of surface is mu naught c over 2 kt. Explain what is meant, what we mean by radiation in this case, and given that the source charge is not localized. Oh, okay, getting ahead of myself. Let's draw this out. Okay, so if we just have some ring in the YZ plane, again, electrically neutral, so it has to have enough positive charge and negative charge to, have a current, so to speak. And then you see, if we doodle everything, radius r for the ring, thickness dr, has some height z. So from the source to a point on the z-axis, that's script r. Again, pretty typical setup that at least we're aware of by now, how to use the notation. So then for part A, what we have to go back to is the integral formulation of the vector potential. So we have mu naught over 4 pi, and instead of a volume current density, we just have a surface current density. But we need to apply it at the retarded time. So this is where we get dA equal r dr d phi. Easy enough. We're just going to push out that d phi integral immediately. And what we see here is that we have 0 to 2 pi for the phi integral. And what we need to do is run to 0 to Rm, or the max R, for the R integral. But we have to evaluate this at the retarded time, and we see that script R is equal to, from the diagram, is equal to square root of R squared plus X squared. So from the first line, we go to the second line, and we take care of the phi integral, and that cancels a factor of 2 pi out. We like that. That's how we get mu naught over 2. We also, in that second line, plug in the retarded time script R, and now we can kind of finagle our way down. But what we need to note here is that instead of k being a vector, we now put the direction z hat. So that's fine. But the important part here is that the integral has to go from 0 to the Rm. And the maximum R that we can have is given with relation to the retarded time. So t minus that square root r squared plus x squared over c has to equal 0. Okay, so let's be aware that news will not travel outside of that particular setup from 0 to Rm. We don't know what's going to happen before that because it didn't reach us yet. That's what it's saying. So R max, once we solve this retarded time, sets us up for R max equal the square root of ct squared minus x squared. Not terribly inconsistent with what we've seen before. And then we have kt equals 0 for t less than 0, so we don't need to have anything in the negative, like negative infinity. So we just carry it through. The reason why we do this is now we have two different distributions. So for the first one, that's just a constant, so that's why we put out the k naught. And we just have r dr over r squared plus x squared. Allow that integral to carry through. Again, that calculus is not too hard. We're just left with rm squared plus x squared minus 0 plus x squared. So if we plug in rm squared, then we get c t squared minus x squared plus that x squared, so those x squareds cancel. And then we're eventually left with a ct minus x in the z-hat direction with the constants mu naught k naught over 2. All right, so fields exist only when ct is greater than x. again, the news can only travel at the speed of light. So if we're further away, then we just haven't, if we look at somewhere further away, we just haven't observed that information yet. So with that, we have that condition, CT greater than X and 0 for CT less than X. So the field is a negative time derivative, easy enough. We just get a factor of C there and the negative sign. B is equal to the curl, so we only need to take the derivative of the AZ direction in the X with the X derivative, and that curl gives us a Y direction. So we see that we get mu naught K naught over 2 and a Y hat. All right, fair enough. For configuration 2, though, instead of a constant in time, we have a linearly increasing in time. So instead of having a 1 in the numerator, we have a t minus the script r over c in the numerator. And now we have to split up the integrals into 2 different parts. That's fine because the second part cancels out to 1, and we like that. Well, the fraction cancels to 1, and you're just left with r dr. So that goes to r squared over 2. The other one is the same as last time. So we just have a t times ct minus r, or ct minus x, with mu naught alpha in front as our constants. And then we just have a 1 minus c over, with a ct squared minus x squared over 2. Again, integral calculus, not that terrible here, once we set it up, of course. Now, in making this tidy, we factor out a 2c from that second term. And so we have to put in a 2c in the first term in order to make everything work out accordingly. Which, again, not too bad once we consider how they cancel in the next steps. But with that, let's just go ahead and be careful to do cancel away. And then what we see here is that looks like the square form. So we factor it out. And so what we say is that the potential here is mu naught alpha over 4c x minus ct, the whole thing squared in the z hat direction. Again, fields only exist where ct is greater than x and 0 for ct less than x. So with that, take the negative time derivative. Easy enough. You get a factor of 2 from the power rule and a factor of negative c from the chain rule. So the negatives cancel, and where that 4c goes to 2. So the electric field is mu naught alpha x minus ct over 2 in the z hat direction. Whereas B, again, just a curl. We go to the y direction. We have that negative attaching. And the x, you have to take the 2 down from the power rule. But we don't have anything else to multiply for the chain rule, so we're good to go. Now all we need to do is need to form match for part B. So if we let u equal r squared plus x squared minus x over c, then du, which is, go ahead and take the derivative, is equal to 1 over c with the bracket term of 1 over r squared plus x squared r dr. Okay, so so the retarded time, t minus script r over c with the script r in there. All we have to do now is add a x plus c and a minus x plus c, because we know we can add a 0 and not affect anything. And with that, we have a plus or minus there, and that allows us to put in a u, hence the t minus u minus x over c. And, this actually works out quite well. So with that, if r goes from 0 to infinity and u goes to 0 to infinity, because it follows through, we're allowed to recompact that scalar potential, or the vector potential, from the original formula to mu naught c over 2 z hat 0 to infinity k as a function of t minus x over c, because we put that in, minus u du. So we were able to prove that. Then if we want the fields, we just take the minus time derivative, so we push that through. And now we have to evaluate what that partial derivative is of the k. And if we do that in terms of, and then we have to equate that in terms of what happens to the u. And again, we can match these because d by dt of k is equal to negative d by du of k as well. Okay, we get the same result there. So now we plug everything in terms of u, since we're integrating with respect to u. And so that negative goes away, and then we just tidy up. So since we're taking the partial derivative with respect to u and integrating with respect to u, fundamental theorem allows us just to take the integrand out and evaluate it at the limits, and that's what we do. So after that, we are left with a negative mu naught c over 2 z hat k from k at the retarded time, which is t minus x over c. How cool is that? And then note that 1 and 2 are consistent with this result. Meanwhile, b is just the negative partial of az with respect to dx in the y hat direction. Following a similar manner, we need to take the partial of d by dx of kt, and we need to put that in terms of what it is to take the derivative with respect to u. We know that with dx, we get a factor of 1 over c out because of the chain rule. And that's what we see here is 1 over c du, d by du of k is the equivalent partial derivative. Put that in and you see the c's cancel, fundamental theorem again, and we see that the b field is equal to mu naught over 2 k t minus x over c in the y hat. So again, consistent. Pointing vector, just take the cross product of u of e and b. You see that the mu's cancel, no big deal. And then we're left with a negative z cross y after we get the k function squared. We see that z cross y gives us negative x, but we already had a negative there. So we get y cross z in the anti-commutative cross product. So it tidies up nicely to x hat. And then what we have to say is that this is the power per unit area that reaches x at time t. It left the surface at time t minus x over c. Moreover, an equal amount of energy is radiated downward. So the total power at the surface at time t is mu naught over c divided by 2, since we have twice, kt squared. Okay, not too bad, but definitely a little bit of a mental work with the retarded times.